transfer in GMAW.
Thank you very much. All right, yeah, so here to present this project. We're applying deep learning to characterize the arc and metal transfer, specifically droplet characterization for gas metal arc welding. So this work was done in conjunction with Lucas Ramos, visiting student from Peru, specialized in machine learning, to develop this model with me. Okay, so when we're doing welding research, specifically with gas metal arc welding, we acquire a lot of data through high-speed videography, right? And when we're looking at these high-speed videographies, we're often limited to a qualitative analysis of these videos. So the intent here is to how can we quantify the data that we're obtaining from these videos. So the goal is to develop this model so we can correlate the voltage, the arc length, and the current, right? As well as quantifying the metal transfer. The challenges here, as I mentioned, we're often limited to the qualitative analysis of these videos. Just because this process is quite iterative, it's quite cyclic and it's erratic. And also, there's a subjective arc length definition here. I just put some previous work from other authors with a very just portraying the subjectivity in these arc length definitions, which definitely contribute to the challenges. Now, the solution here that we're proposing is a physics-based model for voltage, and implementing this deep learning algorithm using UNet to process large amounts of the data from the high-speed videos synchronized with our data acquisition, voltage, and amperage. So first, I'll just go through some definitions. On the left-hand side, we have one frame from a high-speed video. And on the right-hand side, a diagram. So I'll refer to this diagram as we go through this presentation. So starting from the top, we have the contact tip. Over on the left, you can't see it because it's behind the nozzle, but it's right here. Next, you have the electrode extension, where you can see right above the molten consumable. Here you have the workpiece. Next, you have the weld pool. So the next few regions I'm going to show are the regions of interest for our model that we're going to segment. So first is the molten consumable, which is essentially the droplet that's forming, that's not yet detached. That's highlighted in orange. And then you have the droplet and the spatter, which we will highlight in red. Then the arc region is divided into two distinct regions. First, the internal core, which is primarily composed of metal vapors, and the external region, which is primarily composed of shielding gas. So the metal core, here we're going to highlight it in yellow, and then the outside, which is the external cone, we'll highlight it in blue. Everything else, we're going to label as the background, as it's not of interest to us at this particular time for this model. Okay, once we have these images segmented, now we can start extracting some data. Here, I'm showing how we are quantifying the droplet size. So as these droplets come into contact with this horizontal line, as we're processing these videos, for every frame that droplet intersects that line, we're gonna count, or we're gonna measure the cross-sectional area of that droplet. So here you see before the intersection, during the intersection, and after the intersection. That's how we're counting and getting a representative size for each droplet. Now, how about distances? To measure distances within the arc, you need attachment points. So these attachment points, we're putting everything on a coordinate system, so every attachment point that we define will have an X and a Y coordinate. And the software, the way that we develop the software is we said, okay, we're gonna have user-defined reference point and a datum point. The reference point is simply a point user-defined, as I mentioned, right above the multi-consumable, and it's in the middle of the consumable. The datum is simply the location where the droplet comes into contact with the weld pool. So if we draw a line between these 2 points, we can now divide the arc into two regions, the left and the right. So that if we can obtain the maximum or the highest point of each color, then we can take an average of the Y coordinates to get an average arc length from the datum. Okay, so now the contact tip to workpiece distance, we define that as part of the experiments, so that's fixed, so that's a known value for us. So now we can start extracting some data. So here we have the external arc. Again, we're finding the maximum points from the two regions. If we take the average, we find the characteristic distance, the arc length distance for the shielding arc region. If we repeat the process for the multi-consumable, at the top of the orange here, we will obtain that respective characteristic distance, and if we recall back to the contact tip to workpiece distance, the difference between those two will simply be the length of the electrode extension. Again, that's the distance between the contact tip and the top of the molten consumable. If we repeat the process for internal arc, same thing, we get its respective distance, and then the tip of the molten consumable, that is just a singular point, we don't need an average, and that's defined, shown as here. Once we have all these points, it's very easy for us to obtain a length of the molten consumable, which is right here, from the tip to the top. Great, so our experiments, this is our experimental setup. We have our welding machine hooked up to our data acquisition system. We have voltage and amperage transducers. We have our high-speed camera pointed perpendicular to the arc, so we can get a nice cross-sectional view of the arc region. And all of these experiments were carried out with aluminum. We used ER4043 consumable, and our base weight was 6061. So here's all the welds that we recorded. On the vertical axis, we have the voltage set at the machine, and on the horizontal axis, we have the wire feed speed set at the machine. All these points, the different colors and shapes, they pertain to the different contact tip to workpiece distance, as we have to adjust it to account for the different arc sizes. And I want to draw your attention to these values that are above the markers. So this is the number of frames that we collected in just over a second. So it gives us a true representation of what's going on inside the arc, as it is a very erratic process, right? The arc moves up and down throughout a given weld. Okay, so now this is the deep learning, the architecture that we use to process our videos. Essentially, it consists of a raw image that gets input. It extracts characteristics of interest as it encodes, and then it decodes to reproduce this segmented image with the colors of interest, or with the regions of interest. Okay, so in order to train this model, we manually segmented these images. We segmented a total of 1,021 images. So from the 1,021, we used 800 for training, 200 for validating, and 21 for testing. For the 800 images that we used for training, we performed some data augmentation with a multiplier of 10 times 10 to obtain 8,000 images. Essentially, we just changed the brightness, the contrast, the scale, and rotation translation in order to obtain more images from our data set. Here on the right-hand side, we have a plot that shows the spread of the welds that were performed and the training images that were where they belong in this map. So here in the legend, you have the training images in blue dots, and these numbers here add up to 1,021 images. The red squares are the videos that were processed, so you can see the spread between the training and the process videos. Okay, so one of the metrics that's key for UNet is this intersection over union. So just quick overview. So intersection over union is the area overlap divided by the area of the union. So if I am telling from my training image that this is the droplet, and my algorithm is telling me that this is the droplet, there's no intersection, so the intersection over union is square root of 0. If it intersects by a quarter, it'd be intersection over union 0.142. By a half, it'd be 0.33, and if it's perfectly overlapped, intersection over union of 1. So for our training results, we see that from the validation and the training, which is these two lines here, we're sitting about 90%. And for the loss, we're sitting quite close to 0, so I'd say it's quite promising for our training. Once we have that training, then we start processing some videos, and this is what they look like. On the left-hand side, you have the raw image, and on the right-hand side, you have the UNet-produced image. And it's quite valuable because now you can get a real appreciation and quantifiable per frame. So here you start to see that this droplet is going to come into contact with that line, and you're going to see this droplet count increase by 1. So now we can start counting the droplets. We can start getting more data in terms of frequency and cross-section of the area of the droplets. Another interesting point that we see here is what happens with the metal vapors, right? The inner cone. As you see, as the droplet forms, the voltage increases up until the detachment point, and then you have a sudden drop in voltage. At that same time, you'll have a slight increase in arc length, which is actually counterintuitive because in welding we understand the voltage is related to the arc length. But it might be true from a macro scale, but when you're looking at each individual cycle, the exact opposite happens, which I thought was quite interesting. It gives you really good insight into what's going on. Now, the droplet property. So here, this is just an example of a histogram, what we can obtain for every single weld, so you can get an appreciation for the distribution of droplet size per welding parameter. If we take a look at all the welding experiments that we did and the respective droplet sizes, you see that as you increase the current, as expected, your droplet size decreases. But for a given current or wire feed speed, as you increase the voltage, we saw that the droplet size increased. Okay. Now, when we discussed grabbing massive amounts of data to get a true representation, I want to just highlight here each one of these markers, just recapping the tip, the length of the arc to the tip, to the internal arc, which is the metal vapors, to the top of the molten consumable, and to the external arc. If you plot this just for, let's say, half a second, you can get an appreciation for what's actually happening, how much changes actually occur during these droplet cycles. So if you were to take a sample and say, okay, for instance, a still image, if I take a still image and I say, okay, well, the top of the molten consumable, the arc length at that point is right around here would be 12 millimeters or just above 12. But if I measure over here, now I'm above 13. So it's definitely important to get a good amount of data to take an average so that you can obtain a representative value. So now if I zoom into just a few droplet cycles to see what actually happens, same diagram, same markers, same colors. Now we can get an appreciation of what actually happens during these droplet cycles and what the interaction is between voltage and these metal vapors that occur at the core. So on the vertical axis, you have the measured voltage. On the horizontal axis, you have time. And on the vertical axis, you have the characteristic arc length. That's on the diagram here. So if I start on the left, these numbers here are just the frame numbers for reference. So if I start on the left, this is right after detachment, right? This is the peak of the voltage. So the peak occurs, you have detachment, and you see that the droplet detaches, and you have no metal vapors, that is to say no yellow attached to the molten consumable in orange. As you progress, the droplet grows, right? You see here the tip of the molten consumable, right? The tip grows, and you have no evaporation attached to the molten consumable. It recoils, and then it starts to grow again up until you have these vapors form and attach to the molten consumable again. Something very interesting that I found here is that as we pass a threshold for length of the molten consumable, you begin to have these evaporations attached to the molten consumable again. Here's an example here. You see that as the droplet grows to a certain extent, you can see it droops down below, lower compared to these two droplets. And here we're effectively seeing these metal vapors form. And then lastly is this last frame here. As the droplet recoils up, the droplet size actually decreases, and you already had evaporation. But as soon as it decreases, all of a sudden you don't see this metal core region attached to the top of the molten consumable. So we found that to be quite interesting, gave quite good insight. Now if we take a look at the average from all of the, if I take a look at all the frames, and I consider, okay, what is the maximum, or what is the length of the molten consumable required in order for me to have evaporation, and I landed at this 1.4 millimeter. You see everything that's in green is where we effectively had evaporation. I'm just showing you 4 cycles, but I took the sample from 115, and this is the 1.4 that I got. And it does give a little bit of insight to where the model can improve, because we're not seeing the evaporation come through here, but in the images it's showing that it is there. Okay, so just a quick, I think we're almost a few minutes. Okay, so just finish up on voltage model and the data that we can extract to correlate these lengths to voltage. So the voltage that we measured includes the cathode, the anode, the contact tip, the electrode extension, and the arc column. Now, the major contributors are the anode and the cathode. As you see on the left-hand side here, I have a diagram that shows the contribution to the overall fall voltage on the horizontal axis, and on the vertical axis, you have the distance from the basement. So the anode and the cathode, approximately independent current, and we'll see that here. Next we have the arc column term, which is also a major contributor, and depends on this constant that you'll see in the next slides in terms of volts per millimeter. Next we have the term associated with the contact tip, minor contributor for sure. Same with the electric extension, especially for aluminum since it has a low resistivity. So again, minor contributor. So this leaves us with two lengths that we require: the length of the arc and the length of the electric extension, but we can already obtain that from our algorithm. So if we put this to work, we have the measured voltage, and if we subtract the contact tip voltage and the electric extension voltage, we get a voltage that is composed of the cathode, the anode, and the arc column. If we compare that to the length of the arc, now we can get an arc column potential, and we see here to be independent, approximately independent of current, because from all the experiments that were performed, from 120 inches per minute to 204, there was small variation. So this is quite convenient for us, because if we're designing a welding procedure, for instance, we can consider this value to be what you would lose in volts per millimeter for your arc. Okay, and just to clue it up here, going back to our voltage model, now we have our voltage that we lose in the arc, the contact tip, and the electric extension. So now the remaining two voltages would be the loss at the cathode and the anode. And here we see that it's not exactly independent current, but it's approximately independent current with an average value of 19.75. So this is important because, again, if we go back to the welding procedure development, we know that we need to have a certain voltage that's required to overcome the anode and the cathode fault voltage, and anything above that would actually manifest in an arc. Okay, so yeah, in conclusion, we successfully trained this deep learning algorithm to gain quantifiable data from the droplets for the droplet size and the arc length. We got good insights to the effects of metal vapors on the voltage measured. We found the arc column potential to be 0.41 plus or minus 0.06 volts per millimeter for aluminum, 4043, and the sum of the anode and the cathode to be 19.75. So we'll continue to generalize this algorithm to process different materials with different welding processes. And more importantly, we're looking to use this as a tool to validate analytical models.
Okay, thank you. We have time for one question, just one question. Okay, so this time I will choose you. You asked not many. Right, okay. Yeah.
My name is Kawhi from the High State University. So what kind of regression model have you used to train your neural network with experimental data? And if you tested overfitting for the data?
Good question. That's more of a question for my colleague, Lucas, but we can talk after.
Okay, thank you.